Hey everybody, we're going to take a look at section 9.3. So we're almost at the end. We've got a couple more lessons to cover. And what I want to get into in this section is looking at confidence intervals and how we can estimate a population mean using a confidence interval. Remember, a confidence interval gives us a range of plausible values for a population parameter. So now we're going to look at something called a t-distribution. And a t-distribution, the idea is very similar to just a regular old normal distribution, but the t-distribution is nice because it works when we have smaller sample sizes. So we don't necessarily have to have a sample size above 25 in order to apply this. So hypothesis tests and confidence intervals for estimating and testing the mean are based on a test statistic that's called I think it's just called the t-statistic. I usually just call it the t. So the test statistic, kind of like the z-score, we could call it a t-score if we want, but the formula that we would use to calculate this t-value would be x bar minus the population mu, whatever that is, whatever we would expect it to be, divided by the standard error that we might have to estimate. So the estimated standard error, instead of using sigma, if we don't know what sigma is, we can estimate it using s. So s divided by the square root of n. The population standard deviation, we don't always know, and so that would be unknown. But we can instead estimate it using s. So if you remember back to when we first did confidence intervals with proportions, we had an estimated standard error using p hat, same idea. Now we have an estimated standard error but using s instead of sigma. The t-statistic does not follow the normal distribution because the denominator changes with the sample size. Depending on what the sample size is, the shape for that t-distribution will vary slightly. Now, it will still be symmetric, it will still be bell-shaped, but it's going to vary slightly compared to just the regular normal distribution. It's got more variation than that z-statistic because that denominator always stayed the same. If the three conditions for the central limit theorem hold, then that t-statistic will become close to a normal distribution anyway. So the t-statistic follows a distribution called I think I was just looking for normal here. So in other words, if the theorem applies, then our t-distribution approaches a normal distribution. That's the idea. And generally, as long as we have a sample size that's over 25, some textbooks say 30, I think ours says 25 though, that t-distribution becomes normal. A couple other properties about that t-distribution. It's, like I said, it's definitely symmetric and bell-shaped. The tails are always a little bit thicker than the normal distribution. The shape depends on the degree, what's called the degrees of freedom. And we might abbreviate that as df. And df is computed by doing n minus 1. So taking the sample size and just subtracting 1. If the degrees of freedom is small, then the tails are going to be thicker. So the tails are going to be a little bit thicker at the ends. If the degrees of freedom increases, then the tails will get thinner. So in the picture below, I have a couple different representations. In this first picture A, degrees of freedom is 1. That means you would have been using a sample size of 2. And you can see that the graph, that's on the one on the inside here. And see how thick those tails are. They're pretty far away from the x-axis versus the regular normal distribution where the tails are much closer to the x-axis. In this picture, my degrees of freedom are 10, which is a larger sample size. So you can see my tails are a little bit thinner. They're closer to the x-axis. And you can see I'm approaching a normal distribution, and that's the idea. This last picture, my degrees of freedom are 40. That means I had a sample size of 41, and I'm pretty much looking at a normal distribution. It's the same idea. So that's why I'm saying once the sample size gets large enough, your t-distribution is going to become normal anyway. And that's what this last point says. As the degrees of freedom approaches infinity or gets larger, the t-distribution approaches the normal distribution. And we'll just default back to that once we get above a certain sample size. Now, how does this relate to confidence intervals? So as previously mentioned in the course, a confidence interval can be interpreted as a range of plausible values for the population, and I'm going to say the population mean this time, whatever the population parameter is, but we're looking at means now. Give us a measure of how well that method used performs. Remember, we would say like we are 95% confident. When do we use confidence intervals? Whenever you are asked to estimate the value of the population mean on the basis of a sample mean. So when we pull a sample from the population and we want to make an estimate for the population mean, what is the typical time a Flagler College student studies per week, for example? So what is the mean time, typical time, average time for all Flagler College students? Do not use a confidence interval if there is no uncertainty in your measurement. Uncertainty in your measurement. So in other words, if you have data for the entire population, there's no need to do a confidence interval, right? The point of a confidence interval is to estimate information about the population. So if we have the entire information about the population, then we don't need to do the confidence interval. So conditions to check for running a confidence interval for a population mean: either you need to have a random and independent sample. The sample needs to be large enough to where they tell you one of two things. Either that the population is already normal, so that's one option, or the sample size is at least 25. And then you need to have a large enough population so that the population is at least 10 times larger than the sample size. Let's do a quick example here of how we're going to do this. A used car website wanted to estimate the mean price of a 2012 Nissan Altima. The site gathered data on a random sample of 30 such cars and found a mean of 16,610 with a sample, so this is a sample mean, let me point that out. A sample standard mean of 16,000 and a sample standard deviation of 2,700. A 95% confidence interval for the mean was created, and this was what they got. So describe the population. The population would be all 2012 Nissan Altimas, right? That's the only thing I'm looking at, are 2012 Nissan Altimas. Identify the following. So the 16,610, that is the sample mean, so that would be X bar, and since it comes from the sample, it's a statistic. The 2,700 is the sample standard deviation, so that would be S, also a statistic. And then the sample size, N, is 30, also a statistic. Verify that the conditions are met. Let's see, did they say a random sample? They did, so that's good. Is the sample large enough? It's over 25, so that is good. And certainly the population, all Nissan Altimas, there's more than 250 of them. Interpret the confidence interval. So we would say we are 95% confident that the mean price for all 2012 Altimas is between what two values? So remember, that gives you a range of plausible values. So it's between 15,588 and 17,632. Is it plausible that 18,000 is the population mean based on the basis of this interval? And I would say no. Why? Since the 18,000 is not contained in the interval. So that is probably not a plausible value. All right, interpretation of the confidence level. Remember what that 95% tells you. It tells you that if we were to do this again and again and again, take repeated random samples. So if we were to do, say, 100 random samples of the same size from the same population, we would expect 95% of them, or if I did 100, that would be 95 of them, to contain the true population parameter, and 5 of them would not. So keep that in mind, that if I were to do this again and again and again, 95% of the confidence intervals I come up with should contain the real population parameter. Now, if we were to compute this by hand, how would we do this? If you remember way back when, you don't have to write this down, but the population, when we're estimating population proportions, our format for a confidence interval is p hat plus minus the margin of error. So when we're doing means, it's going to follow the same format. It's going to be x bar plus minus the margin of error. Now, how do we calculate the margin of error? The margin of error, instead of using z star, remember way back when, it was z star times the standard error estimated. Now it's going to be t star times the standard error estimated. And the standard error estimated is that formula I gave you previously, s divided by the square root of n. How do we get that t star value? Well, that depends on the degrees of freedom. So degrees of freedom, of course, is n minus 1. And so we would get this t star value using either a table. Maybe if you took stats in high school, you might have had a teacher that had you use a table for these t star values, or we're going to use StatCrunch to do that. But just like it did previously, that t star value tells us how many standard errors to include in our confidence interval. And we'll use technology and we'll use StatCrunch to help us do the details of this, but I want you to just kind of see what it looks like. We'll do maybe one in class tomorrow by hand, and then we'll use StatCrunch and look at some of the interpretations. So I'll see you then.